Okay, I guess we are ready to roll. Thanks for coming to the rest of the session this morning. First speaker is Andre Nachbin from IMPA. Yes, I will try to do this. Okay, yeah. So first speaker, Andre Nachbin, dispersive waterways on graphs. I guess congratulations for the victory yesterday.
I didn't do anything.
And okay, take it away. Thanks,
Okay.
Andre. Yeah.
Well, thank you, Roberto. At least I think I'm a very happy speaker today, right? So I hope I managed that. So anyway, very happy to be here, independent of the Brazilian victory. I'm very happy. Thank the organizers. Newton Institute, it's always very inspiring to be here at the Institute in Cambridge. Thank you all for being here. And this problem is a problem that I worked a few years ago, and I'm back on it, and I would like to share with you. As I will show you, this problem is, at least to the best of my knowledge, for dispersive waves on graphs. You see where I'm going to get. There's not much, at least that I know, literature, both on sort of theory and other things in the modeling. And there are some theory, of course, for hyperbolic problems on graphs. And still there's some, I think, issues, some points in the modeling that I will show to you that here we're able to include in this problem in a systematic way, as you will see. So here's the problem. So let's start. We have an open channel with a rectangular cross-section. Okay, let's start with something simple. You can change the cross-section. Let's have a rectangular cross-section. And let's also consider that we have these huge walls. There's no overflowing. So it's like a huge canyon, right? And, oh yeah, the pointers work. So we have an incoming wave. The problem that I will start working is a 2D problem. And what I want to do, my interest, and something that surprised me and got me kind of excited in this problem, is that how to reduce this 2D open channel problem to a graph, and you will see why. And when we reduce it to a graph, then we will need a compatibility condition at the node. Okay, so this is the 1D graph. This is the forked region. I'll show to you what happens. The dynamics is more complicated in this region. Out here, basically, it's like a plane wave. So I'll start. The modeling starts with actually Wu in 1981 had the first problem in doing the depth average potential theory. So averaging, he calls the layer model. So he averages over depth, the potential theory. I'm not going to write the potential theory equations. And then he actually considers bottom variations in time and so on. So Wu, with his collaborators, in 1998 had this this paper that has beautiful figures. I will show you and caught my attention, basically using the reduced model, which is the 2D Boussinesq system, for waves, first solitary waves on channels with sharp turns or high curvature turns. And in this JFM 2015, with a former student, we came back to this problem, and we kind of knew we could do the following sort of additions to the problem. So we used their model. Well, as I mentioned, I find the dispersive literature scarce, and that's why it's good to give a talk here, so please let me know what you know about dispersive waves on graphs, okay? So we used the Boussinesq system, and most models, including the hyperbolic models, do not have information on angles of the graph. And we're able to put the information of angles, as you will see, in a systematic way. So that's already a good thing. And the other thing that surprises me, in the papers you see in the literature, there's not much comparison between the 1D and the 2D model. So I'm going to call the 2D model the parent model, right? It's not potential theory, it's already the 2D Boussinesq system. And my reduced system was going to be the 1D, the graph one, okay? So there's no comparison. And this comparison for us was very enlightening, particularly to get a new compatibility condition, as I will show to you. Okay? So our reduced model includes information of the angle at the branching point. We compare with the parent 2D, and we reformulated, and we got a new compatibility condition, and that's the main objective of my talk, to show you all these ingredients. These are beautiful pictures. I find that from the papers of Wu and collaborators. So this one is the first one on sharp turns. Okay, so there's a solitary wave that comes as a plane wave in this very sharp turn. It makes the turn, sort of washes over the wall, and there's a reflection, and it keeps on going. And later on, there's another paper by then Michelle Tang. I think I don't know if you are a former student of Wu, with collaborators, and did these numerics on branching channels. Okay, where the most of the regimes, and the regimes we're going to be looking at, is narrow channels or long waves, meaning this scale, the lateral width of the channel, is small compared to, say, the width of the solitary wave. Okay, and of course, applications to this, rivers, channels, and so on. And one application that I found quite interesting, I was at a European Geophysical Union meeting, and I met, after my talk, I was talking about just Boussinesq problems, which is something I did most of my career over topography. And this gentleman, very kindly, Carl Harbitz from the Norwegian Geotechnical Institute, came and said, oh, we are very interested in Boussinesq systems, and we use this in Norway. And he told me about tsunamis in fjords. And look at this. In this beautiful place, in exactly this place I found at Wikipedia, there was a landslide here, huge pieces of rock, huge. I mean, the volume, since we're doing the World Cup, a few soccer fields coming down. And if you look at on Wikipedia, I have a hard time actually relating to this, but they say the wave initially, well, please help me, the wave initially had 62 meters. To me, that's more of a splash than a wave. I don't know, but please help me, right? But even if it's a wave or not a wave, look at this. So this landslide was here. It went through the system. Part came here, part came over here. And then here at city A, it had 7 meters high. And because it narrows down, at Tyfjord, 12 kilometers later, it had 16 meters high. And look at this disaster. This is the city before and after the tsunami. You're in this beautiful city. 40 people got killed. So that's why Carl Harbitz mentioned the Norwegian. They're monitoring, they're doing modeling and so on about this. Okay, so here are more figures of their papers, beautiful figures of sharp turns and so on, and different channel widths. And here is the Boussinesq model they are using. Okay, so it's basically a depth average. There's some manipulations to the order of we're used to, like weakly nonlinear, long waves and so on, weakly dispersive. And there's this potential here that I'll call it the reduced potential, because it gives us the velocity field, the gradient gives us the velocity field, but it's not a harmonic function anymore, or else this term here would disappear. Okay, it's a convenient model because then with this potential, you basically don't have to solve for u and v, you solve for phi, and so you have a 2x2 system. And that's how they do this. Actually, for this curved one, they put sort of a boundary fitted coordinate for this case. Okay, sort of for the term. So very nice pictures. Okay, so let's see if there's anything else I have to say here. So it's dimensionless, the wave elevation eta, and the reduced potential. All right, so with Vanessa, former student, we then started looking at the sharp turns and trying to use the technology I'm going to show to you. We repeated so we could learn. We repeated their technology. I mean, doing it in X and Y and using finite difference in the physical domain. And we reproduced this. And to me, my intuition, something was wrong. And I find it very much fun when your intuition is wrong and mathematics simulations give you the proper intuition. And I thought actually the solitary wave going through a sharp turn would have a very hard time. But no reflection. It's still a traveling wave. It goes through this corridor, boom, boom, in the canyon, and off it goes. But as it becomes wider, there's more reflection and so on. And my acquired intuition came, I won't show you for this case because in the interest of time, came after I started using conformal mapping for this problem. Okay, for this case, I won't show you, but I'll show you the conformal mapping for the branching case. Okay, so then the paper of Shi, Teng, and So for the branching channel, these are the figures that I showed you already, the 45 degrees. And this was another point we wanted to address, which is they could only do, because they're doing finite differences, they could only do multiples of 45 degrees. So the nodes would fall, so the reaches would fall on the nodes and so on. So this is 45, 90 degrees, and 135. So you can see nice pictures of the wave, part of the wave making turns and reflections and so on. So this is basically the starting point of the thesis of the work of Vanessa, and this was our goal. Well, since they had this limitation of angles, even though the model is okay for any angle, we said, okay, let's then try to generalize the 2D computations to any angle, right? So that we are not restricted to these multiples of 45 degrees because of the finite difference grid. And understand how to model the reduced dynamics of the dispersive PDEs on a graph like this. And you will see why. Okay, actually you can start seeing why right now. Let me show you. Look at this. I mean, it's basically, we have a waveguide. It's basically a plane wave if you're away from the junction, from where it's branching. So why can't we sort of average somehow or forget the lateral dependence and reduce the dynamics to a graph? The price, you have a compatibility condition, but that's fun, something to learn, and you'll see that looking in, I don't see much in the literature, the 1D model being compared to the parent 2D model. And when you look at that, it sort of gives you ideas on how to do a new compatibility condition. So I'm going to come back to this in just a second. Okay, so this is our goal. So conformal mapping, which is something I've been using for water waves over topography, comes in to play here again, but actually with a new flavor, which is something which I thought it was, that's good. I've been using conformal mapping for potential theory problems, and where I have the Laplacian, it's incompressible with rotation, blah, blah, blah. But why do I have to be locked into Laplace equation? I can use conformal mapping even if my differential operator is not invariant. Who cares? Conformal mapping here is basically a curvilinear orthogonal boundary fitted coordinate system. Just like in other problems, for example, with dispersive waves, I can use Riemann invariants even though they're not invariant. I can use characteristics just as a change of variable, convenient change of variable, though the problem doesn't really have characteristics. So here's just a convenient change of variables using the conformal mapping. And here is why we can use any angle. Because, well, for the sharp turn, we always map our canonical domain is always a strip. Okay, so here's the strip. Here are the pre-images of the corners where the Jacobian will have a problem, which is not conformal. Who cares? You just got to deal with it properly. And so it's a Schwarz-Christoffel mapping. And now we can deal even with, say, a symmetric or asymmetric channel. The Jacobian will take care of that information. The Jacobian will take care of the angle. And this guy is going to be mapped onto this strip with a slit. So no big deal. As you see soon, and I think the next slide, this is actually good for numerics. And I can do any angle because I won't see the angle anymore in my grid. The Jacobian takes care of it. I'm going to show you a very nice picture of the Jacobian using the very nice toolbox by Toby Driscoll. Free and always a good advertisement to teach complex variables and see what conformal mapping does. Okay, so here it is. So basically, using Toby Driscoll's Schwarz-Christoffel toolbox, I can map this basically onto this. Here I just have Cartesian coordinate system. And here, I mean, the mini price to pay, it's not really a price, is that because these two branches here are going to close, basically here I have to put two nodes, one to take care of what's happening upstream on the upper part of the y, and the other node to take care of what's happening on the lower part of the y, right? The y sort of closed, right? If I think of the junction as a y. So it's a double-faced slit, and as I mentioned, now I'm free to put any angle, and here's my grid. Let's see if there's anything else that I want to say. No. So basically the mapping is, if you do the Schwarz-Christoffel mapping, it goes from the canonical domain to the physical domain, and here's my curvilinear orthogonal coordinate system, boundary fitted, very convenient for the problem. Okay. Now, as I mentioned, well, the operator is not invariant anymore. Like the Laplacian is invariant under conformal mapping, right? Laplacian stays Laplacian. Here the operator changes. But then I get a variable coefficient equation. So we get, say, Wu's equation. We change variables from x, y to xi zeta, right? Which would be W would be xi plus I zeta. And the Jacobian appears as a variable coefficient. So now I have a variable coefficient PD instead of a constant coefficient, but of the same kind. Here's just for us remembering how it looks like. I'm going to have the main, always going to be the main reach, 1, branching out in a symmetric or asymmetric fashion. And so let's start solving this problem with the finite difference. Actually, there's many things we can do, as you see in the end, but we use exactly the same numerical method that can be improved as Tang and collaborators, just to keep things similar so we could compare. All right. So here is the Jacobian. I love these pictures. They're beautiful. I mean, I can say I love them if because it's somebody else's code, right? I'm not going to be self-promoting. By Toby Driscoll's Schwarz-Christoffel toolbox. And this is beautiful because, right, the conformal mapping is an elliptic problem to some extent, no local, whatever, but things vary very rapidly and are sort of kind of localized. And then my intuition starts working because my intuition is topography, mountains, and so on. That's what I was doing before. And look at this. The Jacobian now, if I have a channel that looks like this, main reach coming this way, it's basically effectively a piecewise constant object, just like a constant that changes from one reach to the other, right? Has a little bit of this complicated structure here. And at one point, you're going to see, I'm going to say, well, let's kind of forget a little bit this structure here and see if we can get away with it, because basically the wave is long, as the scale of the solitary wave is longer than these rapid variations. And on my graph model, I'm basically going to have a constant coefficient here, another constant coefficient there, and another one there. And this also helps my intuition to understand why we have, say, reflection and transmission at the junction, at the branching point, right? Because of this change of coefficients, okay? So as you see, there's a singularity here that we actually, when we do the conformal mapping, we put it slightly off our domain. So it's something big, it gives the right information. So when we map something that's right here, right, and this angle here is actually where the Jacobian is 0. See, this is the formula for the Schwarz-Christoffel transformation, where alpha j, our alpha j times pi is these internal angles, like this angle and this angle. So depending if it's greater than 1 or smaller than 1, you get a singularity or 0. But these are points where the mapping is not conformal. But again, who cares? When I teach complex variables or fluids, my students say complex stuff with singularities. The singularities are the main players. They're good. Sometimes when I was starting to, oh, the function has bad points. No, right? Singularities are important. There's important information there. Okay, so let's keep on going. So here's an example of a solitary wave coming and reaching here the branching region. Okay, here's the incoming wave, computed in the canonical domain but plotted on the physical domain for better visualization. Okay, it's going through the complicated region and it's coming out. See here behind the dynamics is kind of 2D in that region, but I'm more interested actually in the solitary wave. And as we can see, basically out of this complicated region are coming basically 2 plane waves. Not a solitary wave anymore because energy has been bounced back and forth, but 2 plane waves. So why not then reduce this model to a graph? Because the lateral variations are very small. I can just disregard it, right? Because as we can see from the pictures. So that's what we do in the next step. So here is what I'm calling then the waveguide approximation. Let me call it this way, because there's this waveguide. The wave, after it's out of this branching region, doesn't vary too much in the transversal zeta direction. Let's just forget that dependence. The system now becomes spatially one-dimensional. Here it is. I still have my variable coefficients. I get my Jacobian. This bar means I sort of average it laterally, even though it's not varying that much on the transversal direction. And let's play with this model. Then we need to put a compatibility condition here. And looking in the literature and so on, in 1957's book of Stoker, he has this compatibility condition. I kind of knew that from long ago. And the condition seems okay. It says that at the node, the wave elevation from reach 1, 2, and 3 should be the same. And this is conservation of mass of the flux. What comes in must come out and so on. Okay? So, very good. But we found out that actually this standard well-known condition and used by some, and these are two nice papers I'll comment just in a second. Jakovsky was actually one of the inspiring papers for me long ago. I found it and I kept it for this problem. We show that actually this condition, Stoker's condition, has limited accuracy when you compare it with the 2D model. So, you know, there's like proofs and so on, like this paper by Jeremy, proofs. That's fine, it's important for the 1D model, right? Well posed, whatever. But the condition used, which is the Stoker condition, is of limited accuracy, and I'll show you why, okay? So how did we fix it? And you'll see also why. By looking at the 2D model is that we use a shock condition here, and it improves a lot in the compatibility condition. So I'll show you that, and I'll show you how we got motivated to that point, okay? Okay, excuse me. So let me mention two papers that were kind of inspiring. The first one was by Jakovsky, which is, he has this river network like this, so he has the Y region, the Y like this, the Y like that. I'm mostly we concentrate, we can, you know, there's many things to do, but concentrate this one where the incoming wave comes and then it branches, okay? And the way he analyzed this problem, he uses, it's a hyperbolic system, so it's shallow water. He kind of linearizes it, uses method of characteristics, and with the, you know, the Stoker condition, he keeps on checking information through the characteristics coming in and out of the nodes. That gives him a linear system of equations. He actually linearizes the problem. He considers only the subcritical regime, blah, blah, blah. And basically, out of a solvability condition for a linear system, he gets everything sorted out. But it's you know, it's still a kind of simplified problem compared to our problem. And for this meeting, we want to see the dispersive case. And there's no comparison with a parent 2D model, which is, say, the 2D sum and 9 equations, similar to what Stefano was showing. And there's no information on the angles. And that matters. The other paper is more recent by Jerry Bon and Cascaval, Canadian Applied Math Quarterly. They use the BBM model for basically blood flow, human arterial system. And it's a unidirectional model. They actually end up seeing some reflections. So they use also like the Stoker condition with the BBM model. And they basically analyze different situations. One of them is the Y junction with infinite edges, basically half lines. So the analysis like for, interesting analysis for half lines and putting the information together due to the vertex, the node. And they also do for finite pieces and so on. And they prove that the BBM equation is well posed on finite trees and so on. They have no information on angles, but they mention it should play a role. So that's good news. And it's very nice to see these papers addressing this problem. As I say, I don't know much literature on it, be it theoretical, and I mean, from a more mathematical point of view, whatever. Okay, so here's our model, and then I tested the Stoker condition for a very narrow channel, okay, very narrow channel. So this is the asymmetric configuration. This is the angle, 30 degrees, very narrow channel, or that means, right, L over lambda. So the color code is this. Main reach is 1, this picture. It continues as 2, and the branch out is the red and 3. Here's the solitary wave. Here's where the node is. It's getting close to the node. Nothing's happening in the other two reaches. Fine. And then here it has passed the node. So there's a wave both on reach 3 and 2. And there's a reflection coming back. And this is just at a later time. Okay? And to my surprise, I confess it's still my intuition. I don't know, here it kind of works. But the transmitted wave is actually better than the reflected wave. Right? It's not a solitary wave anymore. But still we said, well, let's try to fix it. It's still, let's try to get things right on the money. And it was very nice to see that when we changed from the Stoker condition to our new condition, we got it right on top of each other. So that was good news. Okay? So learning process by adding things to the model and comparing with a parent equation. Okay, so here is how we understood things. So this is a computation for our 2D model. So you see the plane solitary wave coming into the forked region. And now look at this. I mean, the Stoker condition is not good in a situation like that. Who says that all the waves' elevation are the same, right? In particular, it's very intuitive. It's much easier for the wave to keep on going than to get this sort of a secondary reach. And therefore, there's less of a wave amplitude here than there. So how can we deal with this? So there's a sudden change. They're not the same. So the way we did it is, let's look at the 1D equation. Here it is. And let's write it in divergence form, like this, right? And then impose a stationary Rankine-Hugoniot condition at the node. So when you write like this, right, you see some of these papers by people here, right, when showing dispersive shocks. The interesting thing here is that I don't have a dispersive shock. It would be interesting to see dispersive shocks. That's part of things in the future in a scenario like this. So here's the Rankine-Hugoniot condition. Here's the R, here's the S. And I basically have one jump condition here and another jump condition there. That's going to be the new compatibility condition. So, and it arises as a nonlinear compatibility condition. So basically, to have a stationary shock here, I need S plus to be equal to S minus. And the interesting thing is that when you do this, here's the S, you don't need this dispersive part. It's not coming to play a role. Anyway, to be seen. It's, right, for this case, it doesn't play a role. And here is the new compatibility condition that comes from this guy. Basically, the Rankine-Hugoniot condition with this, imposing this, a stationary shock, you get this, and there's information on the angles through the Jacobian. There's also this nonlinear term that comes in from this sort of momentum equation. And if I disregard the nonlinear part, I get back the Stoker condition, because 1 is equal to 2, 1 is equal to 3, therefore, right, 1 is equal to 2 into 3, right, the wave elevation. Okay, so we then go to not so narrow channels in the symmetric case, and this is for angle 30, this is for 60. 30 is right on the money, 60 is pretty good, already showing that, you know, things could, as the angle increase, deteriorate a little bit. And when we have the asymmetric channel, things get a little tougher. So that's already one point I want to understand. It's like how to improve things, right? In my watch, I have like 4 minutes, right? Stefano asked for 7, which is injury time in the World Cup these days, right? Injury time now is 7 minutes instead of 1 or 2. But anyway, let me wrap up. So how to improve this for greater angles? And conclusions then is this. This is the first water wave model that I know on graphs to have branching angle information built in through the Jacobian for general forking conditions. There's a new compatibility condition that uses this stationary shock. We're comparing the 2D and 1D Boussinesq formulations. Topics of interest. I want to revisit the compatibility condition, see, can we improve it for, why is it for 60 degrees starting to deteriorate? Variations of the cross section, natural variation. There's many things to add. Different nonlinear solutions, right, solitary waves. This is out of my reach. I'm not an analyst, but analysis for this kind of problem. Mr. Chairman, this is just, if time permits. I know it doesn't permit, so I'll skip the next slide. And the injury time is not World Cup style. So thank you very much for your attention.
Thanks, Andre, for a beautiful talk. We have time for just a couple of quick questions. Okay, so I guess the gentleman over there is first.
So this calculation is for branching trees. If you wanted to do a calculation for a general graph, can you generalize your methods? I'm asking because it turns out that quantum waves on networks is exactly this kind of problem, and it's an unsolved general problem to write down the adjacency matrix.
Which one, sorry, I couldn't hear you?
Waves in quantum mechanics.
In quantum, yes.
In a general quantum communication network is an unsolved problem
That's
mathematically.
How I didn't understand, yeah.
Right.
Well, one thing here that the method wouldn't work immediately, and it's one thing to be thought of, is that, for example, one thing that would be interesting is that if you have an island, right, then the conformal mapping, you don't have a simply connected region. It's something I already mentioned, for example, to an expert on multiple connect, which is Darren Crowley, right? But he has a very sophisticated, mapping for that. So it's something that requires some effort in doing. There's many things on the table. So to go to a more general, according to your question, more general scenario, for example, if you have holes and so on, things get more complicated. It might be doable. Right now, I don't know how to do it. Did I answer your question?
Yes, thank you.
So this is a historical remark that might interest you if you don't know it. It's the first computational fluid dynamics on graphs known to me was in the 1920s, and it was Lorentz who had a Dutch government project to estimate the height of a dam which would convert a bit of the North Sea into a lake to prevent flooding. He realized he needed to solve the Navier-Stokes equation for the existing flow, and this was quite impossible for him at that time in full 3 dimensions. But he noticed that at low tide, the water flowed in and out in channels. So he made a network model of the Navier-Stokes equation, and he had a group of people, computers who were at that time people, to calculate the flow, and he could compare it against measurements, and this enabled him to estimate the height of a dam which has withstood all flooding in the nearly century since then. So computational fluid dynamics on graphs started with Lorentz in the 1920s. It's a very interesting story.
Well, thank you. Yeah, I will try. I hope I can find this. I mean, sometimes these
By
old
the way,
things.
of course, this was for flow, not waves, but
No,
still,
yeah, I
highly
mean,
non-trivial.
yeah, and one problem that's very interesting, which is more flows than waves, and I know, for example, Italian group, I think Quartapelli and so on, has very interesting models for blood and so on, but it's more flow than waves. So thank you very much, Lawrence. I'll try to look that up.
Okay, thank you very much again. Further questions can always be asked. Andre is going to be around.
Oops,
So till the end
I
of
gotta leave the microphone.
Okay, so the next
No, no.
speaker now.
Thank you.
No, thank you.
Okay, who's quickly is that?